ready to start with, I don't know what number Badger Dairy Insight this is for winter 2022, but this is our final one for the spring session. And then we're going to be regrouping here over spring and summer and planning our next offerings going into later this year, into next year. But with that, we say the best for last. Dr. Paul Fricke is our presenter today, talking about the randomness of reproduction. Maybe a little bit different take on some of the presentations we had, whereas this is going to talk a little bit more about interpreting data, how to look at data, versus maybe some that's, a project specific presentation that we had earlier in the winter. So I have the pleasure of Paul being both an extension colleague, and he was also my graduate advisor as well. So it's always good to see Paul on the program. So with that, you didn't come here to hear me talk today, so I'm going to turn it over to Paul.
Hey, thanks, Ryan. And thanks to everybody who's joined us online here. As Ryan said, this talk is a little bit different than most of the talks that I give. A lot of times my talks are very data-centric around the studies that we're doing and those kinds of things. This is a talk that I call the randomness of reproduction, and it's very conceptual. And I think the concepts that we're going to talk about are extremely important when we start to think about reproduction on dairy farms. It's a fun talk. When I do this live in front of audiences, it's a lot of fun to do. It's very interactive. It's kind of hard to do interactive stuff online, but we'll see how this goes. So again, my name's Paul Fricke. I'm a professor here in the Department of Animal and Dairy Science at the University of Wisconsin-Madison. I've been here about 25 years, and I have both research and extension appointments in the College of Ag and Life Sciences here. Before I get into my talk, I want to introduce this book. It's called The Drunkard's Walk: How Randomness Rules Our Lives. It was published in 2009 and quickly became a New York Times bestseller. It was written by Leonard Mlodinow, who got his PhD in theoretical physics from the University of California at Berkeley. And in this book, Leonard Mlodinow goes through many aspects of life that contain randomness. And as I was reading this book, I was struck at about how many of these examples that he was giving with regard to randomness could be directly applied to dairy cattle reproduction. So as I go through my talk today, many of the illustrations that you're going to see are adapted from this book called The Drunkard's Walk. So what we're going to talk about today, we're going to start with this. We're talking about probabilities. And probabilities are the measure of the likelihood that an event will or will not occur. And the thing about probabilities is that measuring reproduction is all about measuring probabilities. So that's pretty simple and straightforward. What I have to convince you of is that most people do not think about probabilities correctly. And I know people out in the audience are looking at this going, okay, I get probabilities, but I have to show you that in fact, the human brain does not deal with probabilities very well. Okay, so this is where the fun starts. I love this example. For those of you who've been around for a little while, there was a television show on here in the United States. It was called Let's Make a Deal. And they had a game show host here. His name was Monty Hall. And let me just explain how the game worked. So people would dress up in crazy outfits like this, and then Monty Hall would pick a contestant. And there's 3 doors that you can see here: door 1, door 2, and door number 3. Now behind these 3 doors are 2 goats. So this would be like the animal, the goat. So there's a goat behind 2 of these doors. And there's a very fancy sports car, red convertible sports car behind one of the doors. So obviously the contestant wants to win the fancy car. And so what the contestant would do is they would be pulled up on stage, and Monty Hall would say, pick a door. So for example, the contestant would pick door number 1. And then what Monty Hall would do, now Monty knows what's behind the doors, okay? So what he would do is he would open up, say, for example, door number 3 and show them a goat. So remember, there's 2 goats in a car. So he's shown them a goat. So now there's just 2 doors left. And here's the key question Monty Hall would ask the contestant. Do you want to stay with door number 1, or do you want to switch to door number 2? Now, I want everybody listening to think about that question. Would you stay with door number 1, or would you switch to door number 2? Now, this is where it's really fun to do this in a room full of people, because I would put them around tables. I would have them discuss this around their table, and each table would have to come up with an answer. Intuitively, the human brain thinks that it doesn't matter, right? Because it's a 50-50 chance. You've shown them a goat. There's 2 goats in a car. So you've seen one of the goats. Now you know there's just a goat in a car. So it's a 50-50 chance whether you stay or switch doors. So that's kind of the conundrum that we have to deal with. This woman here, her name was Marilyn Vos Savant. I don't know if she's still alive or not, but she has one of the highest IQ scores of anyone who's ever taken an IQ test. So one of the smartest people on the planet. And she had a Sunday column in what was called the Parade magazine. So when I was a kid, this is before, before emails and all those kinds of things, you get the Sunday paper. And I loved reading the Marilyn Vos Savant columns, because people would write in with all these crazy math problems and all these kinds of things. And so this scenario that I just described to you guys is known as the game show problem. It's also known as the Monty Hall problem. So if you Google those, you'll come up with this. And so somebody actually wrote in this particular scenario to Marilyn Vos Savant. So in the text here, this is just exactly what I told you. Suppose you're on a game show, given a choice of 3 doors. Behind one door is a car, the other 2 are goats. You pick door number 1. The host, who knows what's behind the doors, opens another door, say number 3, which has a goat. He says, do you want to pick door number 2? Is it to your advantage to switch your choice of doors? So this was asked to the smartest woman in the world. And here was her answer. She said, yes, you should switch. The first door has a 1/3 chance of winning, but the second door has a 2/3 chance of winning. Now, just let your brain think about that for a minute. Okay, so the smartest woman in the world has said it's not 50-50. It's a 1/3 chance of winning if you stay with door number 1, but you have a better chance of winning, 2 out of 3, if you switch to door number 2. Now, this happened at a time when every Sunday she would write her column. And again, this is before communication, email, all that kind of stuff. So she said that. So the next Sunday, all of these people started writing back and telling her that she was completely wrong, that she was out of her mind. And these people have PhDs behind their name. This guy is a PhD from George Mason University. This guy's a PhD from the University of Florida. These are mathematical people. I'm glad UW-Madison isn't listed here, okay? So nobody from UW-Madison said that she was wrong. So this person says, you blew it. If one door is shown to be a loser, blah, blah, blah. So they go on, these people are convinced it's a 50-50 chance. This person says, you blew it, and you blew it big, since you seem to have difficulty grasping the basic principle at work here. So it's very condescending, actually, telling the smartest woman in the world that she doesn't know what she's talking about. So then all of a sudden you're reading the paper and you go, my goodness, the smartest woman in the world was wrong. She got this wrong. So then the next week she has to come back and she says, okay, let's explain this. The benefits of switching are readily proven by playing through the 6 games that exhaust all the possibilities. So this is a branch of mathematics, actually. It's set theory is, I think, what they call it. So for the first 3 games, you have to look at all the possibilities. And so this is what she did. She put a grid together like this. So if you think of all of the possible games, there's only 3 different kind of games you could have. The car could be behind door number 1, door number 2, or door number 3. And remember the scenario. If you pick door number 1 and Monty shows you the goat behind door number 3, if you switch in game 1, you're going to lose. But if you choose the door number 1 and he shows you this goat, you switch and you win. If you choose door number 1 and he shows you this goat, you switch and you win. So you win 2/3 of the time, you lose 1/3 of the time. And it's so fun when I do this in front of groups of people, because you show them this and they still don't believe it. They still don't believe this is how it works. She also says that, this is if you switch, this is if you stay. And of course, if you stay with door number one, you only win a third of the time, you lose 2/3 of the time. And so this became known as the Monty Hall problem. Since that time, they've run computer simulations and looked at this, and Marilyn Vos-Savant was correct. Switching is an advantage. So if you're ever on a game show with this scenario, you should switch. That's the thing. So again, this is just a little exercise to show you human brains aren't good at thinking about probabilities. What changed during the game was not the probabilities. It was your knowledge of what was behind the doors. Okay, that's really the fundamental thing. Now, she went on to explain this, and this really caught my eye, and I started thinking, how does this relate to dairy cattle reproduction? Because that's what I do, dairy cattle reproduction. She said, you can prove this to yourself, and you can play this game with another person with these 3 playing cards. So for example, the jokers are the goats, the ace is the card, the door that you want. And you're Monty Hall, so you'd flip those over and you can play this game with your kids. Now, she said there's a caveat here. She says you have to do this a few hundred times to get statistically valid results. That caught my eye. That's very important. How many times do you have to play a game like this before you're confident that switching really gets you a 2/3 advantage to staying? So this is introducing kind of a new concept of repeating these kind of trials, I guess is what we would call them. So I'm going to move to another example then and start to flesh this out a little bit. I want you to imagine a coin flip. So if you flip a coin, you have a head or a tail. What are the chances if you flip a coin, you get a head? Okay, so most people, if you ask that question, are going to say it's a 50-50 chance of flipping the coin and getting a head. Now, the problem with this, or let's expand this example. Back in medieval times, the king would host games of chance in his castle. And if you had very unscrupulous people that would play these games of chance with a loaded coin. So a loaded coin doesn't flip 50-50. It's weighted so that it has an advantage to flip, let's say, heads more frequently. If you're playing games of chance and you know that, you can win a lot of money and steal the king's money, which the king doesn't like. So the question is, how many times do I have to flip a coin to convince myself that it's 50-50 chance of getting ahead? And what I would have you do, if I'm doing this talk live, I'll have people pull a coin out of their pocket. When we used to actually use real money, everybody had coins in their pockets, so they'd pull a coin out of their pocket, and I'd say, okay, I want you to flip the coin 10 times and tell me what you get. Well, guess what? If you only flip a coin 10 times, you don't always get 5 heads and 5 tails. Sometimes if you're really unlucky, you might get 1 head and 9 tails. You might get 6 heads and 4 tails. See how that works? So you can get all those in between. And so again, the question is, how many times do I have to flip a coin to convince myself that it's fair, that it's a 50-50 chance? Now, there was a mathematician, his name was John Carrick. John Carrick lived from 1903 to 1985. John Carrick was captured in World War II, and he was imprisoned by the Nazis. And he's a mathematician, so he had a lot of time on his hands, and he had a coin. He did this very famous coin flipping exercise. So if you Google John Carrick, you will come up with this particular figure. You'll find this figure on the web. So what he did is he said, okay, I'm going to cost, now these are to the powers, right? So this is 10, yeah, I'm going to cost a coin 10 times. When he tossed this coin 10 times, he got 40% heads. Well, is that true or not? Well, it's only 10 times. If he got up to like 50 times, all of a sudden it was 57% heads. So now we're seeing this bouncing back and forth. If he flipped it 100 times, he was only at about 45%. It wasn't until he flipped the coin 1,000 times until things kind of started to level off, and it was about at 50-50. So think about that. You have to flip a coin 1,000 times in order to prove to yourself that that coin flips 50-50, heads versus tails. And guess what flipping a coin is just like? It's exactly like breeding a cow and evaluating a preg check. How many preg checks do I have to do to understand what the true conception rate is in a dairy herd? And the answer is usually more cows than are present in that herd. It's very difficult to measure these binomial kinds of outcomes. So let's keep going here. This guy, Jacob Bernoulli, you can see when he lived here. He was one of a number of people in this Bernoulli family, fathers and sons and brothers, and they were very prominent mathematicians. And he was working in this area of probability, and he came up with what he called the law of large numbers. So that's what I'm trying to talk to you guys about today, the law of large numbers. So he wrote this book and talk about this. So let's look into a little bit of what he was looking into. So Jacob Bernoulli would do mathematical exercises that are pictured here. He'd have an urn, and he'd fill it full of a certain ratio of black and white pebbles. So he would have 3,000 white pebbles, 2,000 black ones. That's a 60-40 ratio, or 60% white. And what he would do is he would shake the urn up really good, and then he'd take the lid off and he'd reach in blindly and just pull out a pebble, and he'd say, okay, this one's white. Then you got to put it back in there, then you got to shake it, and you do it again. So these are called Bernoulli trials. And he was asking the question, how many times do I have to do these Bernoulli trials to convince myself that this is the true ratio of white to black pebbles in this urn? Now, this sounds really arcane. I mean, this sounds like kind of weird mathematical type stuff that doesn't have any application in the real world. So let's talk a little bit about these Bernoulli trials. We need to talk about types of data. Bernoulli trials deal with what we call binomial data. Binomial means two outcomes. So it's any series of trials in which each trial has two possible outcomes, as long as the outcomes are random and the trials are independent of each other. That's important, just with statistics, independent trials. And that's really what we're doing when we're breeding cows. We consider each insemination an independent event, okay? Today, such trials are called Bernoulli trials. And a series of Bernoulli trials is called a Bernoulli process. So outcomes are usually labeled success or failure. That's exact, and I'm thinking about this and I'm going, that's exactly what we do with preg checks. They're either pregnant or they're open, right? That's a success or a failure. And I thought to myself, as a scientist, that's what I do. I do Bernoulli trials. I do them on cows with dairy cattle reproduction. That's exactly how this is working. So here's the types of data. We have things that we call continuous variables, and we measure these very often. It's a variable that has an infinite number of possible values between two extremes. So what are some examples in dairy science? Milk production. You know, you can have milk production of 55 pounds or 120 pounds, anything in between a low and a high, any integer number between those two. Body weight, feed intake, serum progesterone. These are continuous variables. With continuous variables, you don't need a lot of cows to assess these. In fact, if you want to do milk production trials, you can use what's called a Latin square experimental design, in which you only have 16 cows, and you do the replicates 4 different times, and you can measure very precisely small differences in milk production. So you don't need a lot of cows to assess the effect of certain things on these continuous variables. Bernoulli trials deal with different kind of outcomes. There's usually only 2 outcomes. You can have categorical variables where you have more than 2, but we're talking about a specific kind of categorical variable. It's called a binomial variable. So let's think about some of the things with repro that constitute Bernoulli trials. Pregnancy outcomes. A cow is either pregnant or open when you do the preg check. There's only two. Your veterinarian never does a preg check and says, congratulations, your cow is 63% pregnant, right? That's a continuous variable. This is a binomial. She is either pregnant or she's open. Pregnancy loss. Cow either loses a pregnancy or she doesn't. There's just two outcomes. Calf sex, heifer versus bull. That's a, I can't tell you how many farms I go to that say we've had nothing but heifer calves for the last 3 months or whatever. Then that's kind of the nature of these binomial variables. They kind of look very streaky, like you get a lot. Twinning is another one. If you talk to farmers about twinning, oh, we don't have twins, and then all of a sudden we have a lot of twins, and then all of a sudden we don't have twins again, and we have a lot of twins. That's kind of the nature of this binomial outcome. They're either going to have singletons or twins, or we could say singletons versus multiple births, right? Cow either ovulates or not, to say, for example, when we give her GnRH treatment. Luteal regression, she either regresses to CL or she doesn't. So many of the things that we're interested in with reproduction involve these binomial outcomes. And so they're very difficult to measure because we need large numbers. Remember what we're talking about. Bernoulli had the law of large numbers. Now, let me give you a practical example of what Bernoulli was doing. So he was doing these arcane pebble, trials with pebbles. But here's a practical example of this kind of mathematics. So suppose 60% of the voters in Basel, Switzerland support the mayor. That's the real truth, okay? How many people do you have to poll for the chances? And here's where Bernoulli got off track a little bit. He wanted to be so sure, he wanted to be completely sure beyond a shadow of a doubt. So he set the surety at 99.9%. Now that's important because we don't need to know within 0.1% the truth. And I'll show you that in just a minute. So the chances are 99.9% that you will find the mayor's support to be between 58% and 62%, okay? What he calculated is that he had to have 25,550 people to establish that amount of surety that 60% of the voters supported the mayor. That was more than the entire population of the city in that day. He got very frustrated with this whole mathematical exercise and said it can't be done. He kind of quit working on this. Now, let's use an example today. Today, we can achieve a statistically significant result with an accuracy of plus or minus 5 percentage points by polling a relatively small number of people. And I think many of you know this. If you see these political polls around election times and those kinds of things, you'll always see within a margin of plus or minus 4%. That's because statistically, based on these binomial outcomes or this Bernoulli example, you don't have to poll the whole population. You can poll relatively small numbers of people and get within a reasonable amount of accuracy what they're thinking as far as how they're going to vote. Okay, the thing you sacrifice is it's plus or minus 5%. Okay, so this is a good example of a practical Bernoulli example. Now, so I'm talking about the law of large numbers. The opposite of the law of large numbers is the law of small numbers. And this is where dairy farmers run into problems. It's the misconception that a small sample size accurately reflects underlying probabilities. I think my experience with dairy farms is that it's human nature. Every dairy farmer wants to prove to him or herself that something works on their dairy, on their cows. You know, they may look at results from a well-designed experiment with lots of cows, all those kinds of things. They'll go home and they'll run their own experiment. But when they do that, they're often dealing with the law of small numbers. This is a misguided attempt to apply the law of large numbers when the numbers are not large. And again, I don't blame people for wanting to prove to themselves that something works on their farm. It's simply difficult to do or impossible to do on some farms based on the number of cows that you might have. Now, statistics help us to interpret data. We can do this under field and experimental conditions. So I want to go into this a little bit and show you guys how we use statistics. So this is a statistical concept called a 95% confidence interval. If we could measure every animal in the entire population of animals on planet Earth, there would be no variability. We would know the answer exactly, but we can't do that, right? So whenever we're looking at data, we're looking at a subpopulation of the wider population. So a confidence interval gives an estimated range of values, which is likely to include an unknown population parameter. And so this is our normal distribution. A 95% confidence interval is going to say 95% of the time when we're measuring from this population, the mean is going to fall somewhere in this yellow part here. You'll miss some of the tails out there. So only 5% of the times will you get samples out in these two extreme sides of the population. So many people then use computerized software programs. And this is another little thing that I run into a lot on dairy. So this is an example of Dairy Comp 305, a program we use here in the United States a lot. If you just run this command, bred sum by breeding code, farmers are basically recording breedings on different things they're doing with different programs. So here we've got this little acronym. It stands for CEDAR. Well, we know what CEDARs are. CEDARs are progesterone releasing devices, a controlled internal drug releasing device that we can put into the back end of a cow, releases progesterone. So people be using CEDARs. This is an OBSYNC program, uses a resync protocol. These are cows bred to a standing heat. These are cows bred to a timed AI program. And these are vet palpation. I think these were probably cows that were bred because the veterinarian told them to, by the way, which is usually the worst conception rate on the dairy. So you don't want to do that. My point is that this is not a controlled randomized trial. They're just doing these different things. The bars, this is the mean, for example, and this black bar is the 95% confidence interval. So I generally say, as a rule of thumb, if you go down as far as you go up, if these overlap, you cannot say that they're different. So for example, the conception rate in the CEDAR group here is 48%, and the conception rate of the OBSYNC resync is only 37%. Most people would look at that and say, wow, CEDARs are doing great. Now, keep in mind, they're not randomized. We don't know why they're putting CEDARs in certain cows. This is not an experiment. But people would logically conclude whatever cows are getting the CEDAR are better than these OBSYNC resync cows. But let's look at this. There's 2,420 cows in this bar, so that the 95% confidence interval is really small because this is a power. It's dependent on the number of animals. There's only 117 cows in this group, so the 95% confidence interval is wider, and you can see they both meet at 39. So statistically, we cannot say that those two things are different. I think this is an important concept when you're looking at field data, to know whether bars are actually different or not. There's so much variation in this bar that it's not different than any of these other ones. You can't say that this is even 50% because the confidence intervals almost 50 to 100%. I don't know how many cows are in the vet palpation group. Probably hardly any. So this is an important concept when you're looking at data. So that's just an example from field data. I want to do an example for some of the things that we do in our experiments, and I want to talk a little bit about experimental design. When we design experiments, there's really three critical components to design an experiment. You need to randomize cows. Let's say you're looking at two treatments. You have to randomize the cows to treatment. You can't put all your favorite cows in the treatment you think is going to be better. Okay, that's not how randomization, we flip a coin and we say one goes this way and one goes this way. You got to randomize cows to treatment. Most farms, if they're looking at something, don't randomize cows to treatment. You have to replicate the experiment. That's really what we're talking about here. You have to have enough cows to determine a predetermined difference. And we use what we call statistical power calculations, which I'll show in just a few minutes. And we always have a control group. So you have to have something to compare it to. You can't switch everybody to a new thing and then conclude that switch actually made the improvement. So you have to have a control group to adequately test and interpret the hypothesis. So that's how we approach experimental design. In my lab, we do a lot of on-farm research. In fact, this Friday, we're going out to a dairy to set up a trial that will do exactly these kinds of things. So remember, I talked about a sample size calculator. These things are all over the web, and I just put this one up here, and you guys can go to that particular website. You don't want to switch these things around, but this is an example where you say, okay, we think that the control group's going to have a 40% conception rate. That's 0.4. We think the treatment group's going to be better. It's 0.6. And so you can calculate then, this will tell you how many cows per group do you have to detect a 20 percentage point difference. So let me give you an example just of how we do this. One of our experiments we did a long time ago, the hypothesis was that double off-sync, that's a reproductive program, and timed AI yields more pregnancies per AI, so that's conception rate, than AI to a detected estrus in high-producing Holstein cows. That's our hypothesis, okay? That's what we want to test. So we said, okay, let's do a power calculation. How many cows do I need to enroll per treatment to detect a 10 percentage point difference between treatments? And we want to detect that at the 0.05 level. That'd be kind of like this 95% surety that I was just talking about. So a 10 percentage point difference. How many cows per treatment do I have to do in a randomized control to get that? So let's say, for example, we think the double off-sync program's going to have a 50% conception rate. We think the estrus group is going to have a 40% conception rate. The cows required per treatment, based on the power calculations, a little over 300. So you need 600 total cows randomized to these two treatments, run at the same time with the control group is obviously the estrus group is the control group. So you have to run your experiment. And this tells us if we want to detect a 10% difference, then we have to have a little over 300 cows per treatment. Well, we did this experiment. This is an experiment that we did back in 2017, published it. We had cows assigned to a double off-sync program that looks just like this. So here's the first off-sync. Here's the second off-sync. We include a second prostaglandin here. That's what makes this a fertility program. Do the timed AI. We compared it to this treatment, which is mostly just 2 shots of prostaglandin 14 days apart. And then they came into estrus and the cows were inseminated to estrus. And lo and behold, the difference was exactly 10 percentage points, very close to what we estimated it would be, 49 versus 39. And this was significant at less than P, less than 0.05. It was actually P less than 0.02. So we can actually say we were just right about at that 300 cows per treatment. So this is how we do experiments. So first thing you have to know, how many cows do I have to include in the experiment to do this? Now, let me give you another example, because farmers are interested in differences that are less than 10%. So let's say, for example, you have a question about GnRH products. So let's say GnRH product A, here's your hypothesis. You think it's better than GnRH product B when we use it in a double off-sync program. I get this question all the time. Product A versus product B, which one's better? Now, let's think about how big of a difference there might be between products. They're exactly the same molecule, sold by 2 different companies, sometimes in different solutions, different salts, that kind of thing. You wouldn't think there'd be a big difference, and actually there's not. So here's our power calculation. How many cows do I need to enroll per treatment to detect a 3 percentage point difference between treatments with alpha equals 0.05? Now, many of you are thinking, you run farms and you say, yeah, 3%, that's a big deal in our dairy. If we could have 3% more pregnancies because we switch products, that would be great. But here's the key. How do you know that 3% is statistically different? It's truly different. It's not random. It's not just a matter of chance. So if you were to do this experiment and run this power calculation, so you're going to say GnRH product A is 50%. Let's say we want to switch to B. We're expecting a 3 percentage point increase. Are you guys ready for this? You would need 4,356 cows per treatment. You need 9,000 total cows in the experiment to run this experiment and determine that it's 3 percentage points different. Most farms are never going to do this. A lot of farms don't have 9,000 cows on one site to run this kind of an experiment. So what you can see is that the smaller the difference we want to detect, the more cows we have to include in the experiment. And that relationship is not, it's not linear. As the percentage goes down, the numbers go up kind of exponentially. These are very difficult questions to ask in research trials. I'm not very interested in running a research trial like this because the chances of there not being a difference are really high. Okay, so 3 percentage points may seem like a big deal. It's just very difficult to detect that particular difference. Okay, so that's a little bit about experimental design, about thinking about field data and those kinds of things. And I hope you're seeing this concept with the randomness of reproduction. So I want to switch gears a little bit, and I want to talk about roulette. And when I do this talk live, if people will actually be honest, I ask the question, how many of you have ever played roulette? You know, most people are familiar with a roulette wheel. And I happened to be in Las Vegas visiting my brother-in-law and sister-in-law, and we went to a casino. And I stood at the roulette table and kind of watched for a while. And there's some very interesting things because statistics and probabilities, if you know about statistics and probabilities, you're a much better gambler. And what I want to talk about is something that's called the gambler's fallacy. Again, it plays on this idea that the human brain is not very good at thinking about probabilities and statistics, okay? So here's the gambler's fallacy. It's an idea that an event is more or less likely to occur because it has occurred or has not happened recently. So if you go to a casino and watch the roulette table, every casino and roulette table has a little electronic board that's up above it. And that board keeps track of things. It keeps track of how many odd numbers are in a row and how many black or red numbers or even numbers are in a row. And so guess what happens at the roulette table? If you spin the table and all of a sudden what happens, you go black, and then another spin, black, and another spin, black, and then another spin, black. Guess what everybody does? Everybody starts betting red like crazy. They start betting on red because what are the chances you're going to get a fifth black in a row? That's a different question. So remember that each spin of that wheel is independent. It's not dependent on what happened before. And so they use that information that they provide at the roulette table to mess people up. And they take a lot of people's money by doing this. When you spin that roulette wheel, your chances of getting a red versus a black are 50-50, no matter how many black ones came before it. That's the reality. It's hard to think of it that way, but that's exactly how this works. So let's think about this again. We're getting a little closer back to our repro examples. This guy is a mathematician. His name was George Spencer Brown. He looks very much like a mathematician, like some mathematicians that I know. He said this, and let's just think about this. He said, in a random series of 10, get this, 10 to the 1,000,007th. Why 1,000,007? I have no idea, but it's 1,000,007. So 10 to the 1,000,007 zeros and ones. So it's just a random sequence, long sequence, okay? 10 to the whatever, 1,000,000th. That's a lot. He said, despite it's a random series, you should expect at least 10 non-overlapping subsequences of 1,000,000 consecutive zeros. Now, again, I want you to just think about that. What if you're a veterinarian and you're doing preg checks in the middle of 1,000,000 consecutive open cows? This is how kind of these random sequences work, okay? This is an extreme example. So let's turn to dairy cattle reproduction. And I love to do this because I get a lot of emails from people And I take their names off of these things because, you know, to hide the names to protect the innocent. So this is an actual email that I got. So let's dive into this. Hello, Paul. Really good to use my name. That really draws me in. Okay. My question, got 160 cow dairy. Immediately, I'm reading this. Okay, 160 cow dairy. Law of small numbers. This is not the law of large numbers. This is the law of small numbers. 160 cow dairy. I've worked with them for about 15 years. They've never had good repro, but did get cows and heifers pregnant. Very good. Herd checks are every 2 weeks. Okay. And every 2 weeks, they check from 16 to 25 cows each time. That would be very typical for 160 cow dairy. 16 to 25 preg checks, that's pretty common. Is that a lot of preg checks? No. This is violating the law of large numbers. So we've had at least 50% be pregnant at that exam. So everything was cool with repro. That's what they're saying. But here we go. Here's the crisis. This is a repro crisis on this farm. For the past 6 weeks, we have only gotten 3 total pregnancies. Call the reproductive expert. We're having a repro disaster on our hands. And I can't tell you how many times I've been doing this for 25 years. Early in my career, people would email me and they'd say, oh, Dr. Fricke, you have to come to our farm. You just have to come to our farm. And so I'd say, okay, when's the next herd check? I did this for a while. I can't tell you how many farms I went to. I showed up, they were having a repro crisis. And the day I was there, guess what? Herd check was fine. Oh my gosh, we don't have a problem anymore, right? So we got to think about this. And this gives us some keys about how people think about reproduction and ways that we shouldn't think about reproduction. So let's just take this example. What I did here is I put this figure together, and this figure represents 200 pregnancy diagnoses. Now, it's 200 a lot. It's more than 16 to 25. You know, I could have done 2,000, but the figure would have been really big. And so the figure consists of black and white circles. And we're going to start at the upper left and move across here, just row by row. So these are like preg checks, okay? The white circles are pregnant cows, black circles are open cows. So there's 60 in this grid, there's 60 total pregnant cows out of 200 total. So what we can say about this is the true conception rate of this population of 200 cows is 30%. But most farms don't do 200 preg checks. Okay, so just let's look how this goes and see if this sounds familiar to you if you're doing preg checks. So we got open, pregnant, open, open. Things are looking bad, but now we got pregnant, 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 pregnant. Oh wow, good herd check, right? Open, oh, not looking so good. Pregnant, pregnant, looking better. Open, pregnant, open, open, and then you get done with this one, and all of a sudden we get here and we go. Open, 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 open. Oh, it's like, oh my gosh, call an expert in. We're having a bad herd check. This is exactly what a herd check will look like. If you're 50% conception rate, every other cow isn't pregnant. It just doesn't work that way. You have streaks of pregnant cows and open cows, and it looks just exactly like this. So let's say that a herd doesn't do 200 pregnancy diagnoses. Let's say a herd checks 40 cows out of this population. If you check this 40 cows, your conception rate that week is only 13%. Now remember, the population was what, 30? So 13%, that's not very good. So bad herd check. You got a bad herd check day. Blame the veterinarian, blame the breeder, call Fricke, get him out here, fix the problem, right? But what if you check those 40 cows? Well, now we're at 23, not quite 30, but better than 13. And what if we check either of these 40? Now we're at 40%. Wow, that's 10%, 10% better than the 30%, right? And so here's what happens when we're dealing with these series of binomial. This is like a Bernoulli process, right? You'll see a lot of variability from week to week in preg checks. If you have a 50% conception rate, it's not just 50% exactly every week. Some weeks it might be 30, and some weeks it might be a lot better. Even if you check 60 cows, so if you check these 60 cows, it's still not the average. You can pick out different sequences in here. So even here, checking 60 cows, it would only be 20%. So let's review. According to the mathematics of randomness, that's what we're talking about, the mathematics of randomness, runs of pregnant or open cows are to be expected in a series of 200 pregnancy outcomes. Ryan, was there a question? You just popped
Finishes. I got a question for you, but finish this slide.
I'll finish this slide. The predictive ability of smaller sample sizes violates the law of large numbers. So most people simply don't have enough cows to really estimate these things. And here's the interesting thing about the human brain. The human brain is a pattern-seeking organic device. Everybody is trying to filter reality and figure out what's going on. Once the human brain thinks they see a pattern, they don't let go of it. And these are the farms that I go to where people say, I've had nothing but heifer calves for half a year. And you look back at their records and you say, well, here was a heifer calf. You know, and so what happens, the human brain, if they get in the mentality that all we're having is bull calves, they might go bull, 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 bull. And, oh, there's a heifer, but whatever. That doesn't count. We just had 4 bulls. You know, so they get this bias in their head. So this is kind of where we're going with this. Ryan, you had a question.
Yeah. So I think a little of where this comes from, and you've talked about continuous versus binomial data. So continuous, we can monitor daily milk weights, daily feed intakes.
Yep.
And so I think with that information readily available, there's, we want to be on top of things. We see, intake drops, we see milk drops. We want to get on top of the problem before it snowballs and gets worse on us, right?
Absolutely. Yep.
So with Repro, we're challenged with it's a completely different type of data, getting enough observations. But at the same time, how do you talk people through, when do you say, no, we do have to intervene, or no, we got to wait and see how this plays out?
Yeah, it's a really good question, Ryan. It's probably the most common question I get when I'm giving this talk. How do I know when there's actually a problem? There are statistical process controls that are in most of these computer packages that we use to manage Repro that are like weighted averages. If you look at, for example, conception rate by week, it'll weight that average. So you might get a lot of variability, and I'll show you this graph in a few minutes. You might get a lot of variability week to week, but when you look at a weighted average, it smooths that variability out. So you don't see the radical changes. And then like dairy comp, for example, will look at changes. It uses statistical process control. So if the drop is more than expected, it will actually code the bar a different color. So that's a real change, maybe a real change that happens. Another story I'll tell real quick, Ryan, is I had a guy that went to one of my talks, and he had a small farm, and he made a comment. He said, and this wasn't in this talk, it was another talk. He says, I don't have a lot of cows in my herd. So I have to use the data that you show from big herds to make decisions on my farm. And that was a really smart thing to say, because he's one of the few people who says, I can't prove to myself this works on my farm. I don't have enough cows. So I have to trust the randomized controlled data that people are doing with actual research projects to make decisions. And then what you have to do is stick with the plan and hope that it's working. Now, whether or not things are going bad, I mean, if things go bad long enough, I think we have to start to take action. But I don't want people to panic. What I want to try to get people away from, Ryan, is the good herd check, bad herd check mentality. That will drive you absolutely crazy to try to figure out what's responsible for that variability. And that's what I'm going to show kind of next year.
Perfect.
Does that make sense? Great comment, Ryan. So this is a good comment because it launches me right into this. So this is another email I got. And again, these are fun examples because they're such real world examples. So this is from a veterinarian. Hello, Paul. I'm wondering if you can help us solve an issue we are having with conception rate variability on one of my dairies. It's like, oh no, conception rate variability. Yeah, hopefully you see where I'm going with this after what I've said. So they included a graph of conception rates since the beginning of May. And I'm just going, oh my gosh, okay, here we go. Now here is the, let's go back to this. Once people see a pattern, they don't let it go. So this is exactly an example of this. Here's what this veterinarian said. There just seems to be an almost 3-week up and down variation. We can't figure it out. The dairy milks just over 3,000 cows. Now we're dealing with a bigger dairy. This isn't a 160 cow dairy. This is a 3,000 cow dairy. And we check cows weekly. Breeding is both by protocol and by tail chalk. So let me show you the graph that this veterinarian sent me. Ryan, this is what I'm talking about. This yellow line is a weighted average. So what it does is it takes into account the averages of, I think, I don't know how many data points before that. So what you can see the ups and downs here on the averages. These are the, look at how big the 95% confidence intervals are. They're big because how many cows are they checking per week? Even on a 3,000 cow dairy, it's not lots and lots of cows. But what you can see is here's a week where Preg checked 30% conception rate, kind of an outlier here. It pulls it down a little bit, but then it bounces back. But here's what this veterinarian is doing. They're going, wow, okay, here we are. Let's just take an example. Okay, we're at 48, 50. Things are going pretty steady here. And then boom, we're down. We're down to 40, kind of come back. And now we're down to 30. And then we're back up to 55 and down. And what this dairy was doing is they were looking at this week going, who was giving the shots? Who was breeding the cows? Did the feeder mess up? What's responsible? What they were trying to get at is what is responsible for that up and down variability? And the answer is it's random. It's random. If you try to figure out why these numbers are going up and down the way that they are, you will drive yourself to utter madness, because this is the ultimate picture of the randomness of reproduction. And so you'll just see variability like this. Now, one thing I'll mention, Ryan, if you look at herds that are heat stressed, for example, you'll see this weighted average move way down in June, July, and August. There's not too much. You might see a little bit of heat stress in here, but I would rather look at this weighted average than look at the ups and downs from week to week. Again, what I'm trying to get people away from is this good herd check, bad herd check mentality. Because even if you've got a 3,000 cow dairy, you're going to see a lot of variability from week to week, and that variability is random. So this is what I call the patterns of illusion. It's human nature to look for patterns and to assign them meaning when we believe that we find them. With coin flips, with pregnancy outcomes, with calf sex, I've used that example over and over. I can't tell you how many people say, you know, we've had nothing but bull calves for whatever period of time. So here's the summary. In each case, the longer the sequence you look at, or the more sequences you look at, the greater the probability that you find every pattern imaginable purely by chance. And just to recap, that was my last slide. Reproduction is incredibly important to your dairy. I understand why people really are concerned about repro. They really like to measure it. They really like to monitor it. But it's inherently difficult to measure because of the type of variable that it is. And one thing, the time that most people evaluate reproduction on their dairy is at a herd check. It's just very logical to do that, right? They look at how was herd check this week? I mean, that's just a common question that everyone asks themselves. You go to a farm, they know exactly what their herd check was last week. But your herd check outcomes are going to vary from week to week. So you can't live and die by the good herd check, bad herd check. I think you got to look at a lot of observations across a long period of time. I like to use those weighted averages. Ryan, I think when you see heat stress, you'll see that kind of thing happen. If say, for example, you started breeding a group of cows with semen that's bad in a tank because the nitrogen level got too low, you'd see that kind of really drop off. You'd see some big changes in the way things go. So that's probably the biggest message that I have, is that it's difficult to measure repro. You can't live and die by good herd check, bad herd check. You got to look at these things long term, and you got to think statistically when you're thinking about these different kinds of outcomes. So anyhow, that's pretty much what I had to talk about today, and we'll see if anybody has any questions out there.
Yeah. If you do have questions, now's the perfect time to ask.
Pop the questions in the chat. I was talking before we got this webinar going. I did this talk for quite a number of groups of veterinarians around the upper Midwest here a number of years ago. And I'll tell you what, the veterinarians love this talk because they're the ones that get blamed for the good herd check, bad herd check mentality. And they liked it because, they just say, well, it's random. That's just the randomness of repro. That's what we have to deal with.